In this video, we're going to look at power analysis, but before we do that, we need to generate value change dump file, VCD. So we need to make some change on our setting. So if you go to simulation here, and then we need to check run gate, map, and enable glitch and generate value change dump file. This is the file that we need, and we need to make sure that all signals are selected. And the model that we're going to look at is our neural model. And then we need to select our test bench file. So we can write our name of our test bench file. So it's just test bench neuron. That is our test bench. And then we need to add the test bench file here. Okay. So when we run our simulation, automatically our test bench will run, and we need to compile all of our design. So you can see here our model sim have automatically opened up, and it have automatically compile our simulation, and it will automatically run everything. You can see we have our result here. So everything is done automatically because we have set to do so. And then we need to finish yes. And then now we can see that it have generated our VCD file. So what we can do next, it is to we can go to Power Analyzer, and you can do add. Yeah, if you go to our signals here, Power Analyzer settings, add. So we can add our VCD file. So usually it is on the simulation, so model sim, and then this is the VCD file that we have generated. Open it, and then this is our module neuron, and then we can check the limits, for example from 0 to 100 nanosecond. Okay, and then we can check all of this. So, and then the output file here, you can write neuron dot surf, and then okay. We must make sure that we are using this setting here, and then we can start to analyze. So, and then we can look at our power analyzer here. So summary. So we can see that our total thermal power dissipation is 431.15 milliwatts. Our core dynamics is 2.89 milliwatts. And our core static thermal power dissipation is 411 milliwatts. And this is for the input-output power dissipation, which is 16.97 milliwatts. So we can try to find, for example, if you go to the settings here, you can see the operation condition. We can see that our VCC is 1.1 volt, and our estimated temperature, ambient temperature, is 25 degrees. Now, since we have all the information here, we can calculate the dynamic capacitance. Since we have all the value here, so we have the estimated clock and the operation condition. So let us calculate this capacitor dynamic. So we know that we have the formula for the power dynamic that we found out to be equal. So we know that the power dynamic, let me call it power dynamic, we found out is equal to 2.89 milliwatts. The formula of power dynamic is the capacitance voltage square times the frequency. So this capacitor we want to find, we know that the voltage is equal to 1.1 volt and the estimated frequency is 250 megahertz. Both of this value we have found it here. So this is our core dynamic value, and if you go to operation value, we can see that the core voltage is 1.1 volt and the estimated clock is 250 megahertz. So the capacitance dynamic is going to be equal to the power dynamic divided by voltage square times the frequency. So if we plug all the value here, we will find out the capacitance is equal to 9.55 picofarad. So this is how we will estimate cost, frequency, throughput that we have found it here, and the power dissipation. So on the next video we will try to sum it up on the board.